Hello everyone, today we're going to be graphing piecewise defined functions and finding the limits using the graphs of the piecewise function. A piecewise function is a function with different pieces. So we're actually going to have to graph the different sections of this function. So in f of x, I'm going to have the piece of 4 minus x for this domain. And I'm going to have the function of a constant 0 for this domain. So I'm going to start by graphing here on an xy axis. This is going to be my x-axis and my y-axis. And so I know that for 4 minus x, this is the same thing as just a linear line, except it's not written in y equals mx plus b. My constants first, so I can see this is b minus mx. So b, remember that b is our y-intercept, so I'm going to be intersecting the y-axis at 4, 1, 2, 3, 4. And my slope is -1, right? Because I have an imaginary 1 next to that x. So I'm going to be going down 1, 1 to the right. So down 1, 1 to the right, down 1. Okay. Now this is going to be one piece of my function, except it tells me that the domain is all numbers except for 2. X cannot be equal to 2. So at x equals 2, I know that this is right here at x equals 2. I cannot have a value at 2 because my domain says x does not equal to 2. So I'm going to erase my value at 2. And since I don't have a value there, I'm going to have a hole. So that's what my blue function looks like, okay? Now, it tells me for the second piece of my piecewise function that I have a constant. And that constant of 0 only exists for x equals 2. So at x equals 2, I have the point, the y value of 0. So this is what my function looks like. And now I'm ready to take my limit. So it says the limit of f of x as x approaches 2 from the left. So if I approach 2, right, here is 2. Again, one more time to highlight. If I'm going to be approaching this limit from the left, I'm approaching the y value of 2. Okay? And as I approach the x value of 2 from the right, I'm also approaching the y value of 2. And so because the left and the right side match, I know the limit of f of x as x approaches 2 is 2. Okay? Moving on to my next piecewise function. I'm going to mark off my x-axis. And here's my y-axis. And again, I have two pieces here. I have t squared plus 2. And I know this is going to be a quadratic because of my t squared. Okay? And I also have the value of 1. So that's just a constant. So let's go ahead and graph my quadratic first. So I know that I have a vertical shift upward by 2. So a normal quadratic is like 0 squared, 1 squared, 2 squared, right? That's what a regular quadratic looks like. Except I know that this whole quadratic has been shifted up by 2 because of my plus 2. So I'm going to take every single of these individual points and I'm going to shift them up by 2. And I don't have enough space up here for these, but this is going to be my graph of the quadratic. Okay, and I'm going to clean up this bottom section since we don't need this anymore. Great. Okay, so remember that this quadratic is going to exist on all of my x values, or t values in this case, except for t and 1. So when t is equal to 1, I cannot have a value there. and because my domain tells me t cannot be equal to 1, right? So I'm going to find my value of 1, which is right here. And that means I'm going to have a hole at my function at that t value. So I'm going to create a hole in that spot, okay? Now, moving on to the next piece of my piecewise function, it tells me that when t is 1, I have a value of 1. So this is going to be my point, okay? And now that my piecewise function is done, I'm going to go ahead and evaluate this limit. So it says the limit of g of t as t approaches 1 from the left. So I'm going to be approaching 1. And I'm going to do so first from the left. So as I approach from the left, my yellow line of 1, I'm reaching a y value of 3. Okay. Now same thing on the right side. As I approach t equals 1 from the right, I'm also reaching a y value of 3. And so because the left side and the right side match, I know that the limit of g of t as t approaches 1 is 3. Okay. Moving on, I have one more piecewise function, and this one has 3 different pieces. So let's go ahead and get started. So for my first piece, and I'm going to go ahead and draw in my y-axis. Oh my gosh, it's so crooked. And my x-axis. Okay, cool. Now, for the domain where r is less than or equal to -1, I'm going to have another quadratic, just a regular quadratic, no shifting up or down. Then I have a constant of 2, okay? And I know that here, this is a linear function, right? This is just going to be a linear or a line with a slope of 2 and a y-intercept of -2. So I'm going to go ahead and get started. So I'm going to be graphing the blue function from all the values where r is less than or equal to -1. So here's -1. So all the values less than -1, okay? For these values on my domain, that's where I'm going to draw my quadratic, right? So I know a quadratic is normally 0, 0, -1, 1, and 1, 1. Add 2, 2 squared is 4. Okay, so this is regularly where my quadratic is, right? This is what my quadratic would look like. However, I only want this quadratic to exist for all the values that are -1 or smaller. So bigger than -1, I'm actually going to erase my function because it falls out of the domain r is less than or equal to -1. Okay, so there is my blue function. Great. Now I have a constant, and remember a constant is just a horizontal line at the value of 2. So this constant is going to begin at -1 and it's going to end at 2. So here is my constant at 2. Okay. And they tell me it's going to begin at -1, except I'm going to have an open circle because I have a less than sign. And it's going to end at the r value of 2. So it's going to end right here. And I'm using a closed circle because I have a less than or equal to next to my 2. Okay, so there's the next piece of my piecewise function. Okay, next I have a line with the equation 2r minus 2. So, and this is going to be graphed on all the values of 2 greater than 2. So all of these values greater than 2 over here on my x-axis, I'm going to have that line. So for this line, I have a y-intercept of -2, and then my slope is 2 over 1. So rise 2, 1 to the right, rise 2, 1 to the right, rise 2, 1 to the right. Okay. So this is kind of what my line looks like. Except again, I only want this line for any x values that are bigger than 2. So over here where I'm less than 2, I'm going to erase this line. And I only want that line to be present for 2 greater than 2. Okay. So once I erase all these markers, stuff, this is what my piecewise function looks like. The blue section that exists where r is less than or equal to -1, the red constant that exists between -1 and 2, and lastly, the line that exists at all values greater than 2. Okay. Now that I have a piecewise function and have a nice graph to look at, I can evaluate my limit. So, first limit, I have the limit of f as r approaches -1 from the right. So -1 is here, and I'm going to be approaching it from the right. So as I move from the right, I'm reaching a y value of 2. Let me get rid of that. There we go, 2. And as I approach -1 from the left, I reach a y value of 1. And so because the limit on the left and the right do not match up, 2 and 1 are not equal, I'm going to say that the limit does not exist. Okay. Now moving on, I'm going to be observing this limit now instead at the y value or x value of 2. Okay. So I'm going to be observing it right here. And I'm no longer looking at this one. Okay. So what is the limit of the function as r approaches 2 from the left? So I'm going to approach 2 from the left. I'm reaching a y value of 2. And as I approach 2 from the right, I'm also approaching a y value of 2. And so because the left and the right side match, the limit is going to be equal to 2. Alrighty, everyone. So as you all saw on that last page when I was graphing piecewise functions, I automatically knew what a function was just looking at the equation. And this is something that I need you all to get really good at, especially once we get into graphing functions really quickly or just knowing the generic shape of a function. So in this page, as you can see, I have most of the function families. I know I'm missing a couple, but these are the main function families that I need you all to be familiar with. And I want you all to know what the domain and range of each of these functions is. And so we're going to do a super quick review. Remember that domain and range. Domain observes the left and right behavior of the function. So what happens as I go toward the left and I go toward the right? And range, and these are mostly like x values, right? And range observes the downward and upward behavior of a function, looking at where the function exists on the y-axis, okay? So I'm going to be observing the end behavior of these functions for the left, right, downward, and upward to find the domain and range. So on this parabola, I know that this parabola, if I go toward the left, is going to extend forever to the left till -infinity. And as I observe what happens to the right, it's also going to keep growing to the right to a positive infinity. Okay. Now looking at the range, as I look at where this function goes downward, there is a stop. It doesn't go downward past 0. So that's the smallest function, the smallest value on the y-axis my function is going to reach. Now, if I go upward on this function, this function is going to keep growing and growing till infinity upward. So there's my domain and range for a quadratic. Now, for a cubic function, looking at the behavior to the left, this is going to keep growing to the left till -infinity. Right, it's going to keep growing until positive infinity. If I look at the downward growth, this is going to keep growing down and down and down and down until -infinity. Upward, this is going to keep growing upward until positive infinity. Okay, looking at a line, for the domain, I'm going to keep growing to the left as I keep growing to the left till -infinity. Toward the right, I'm going to grow toward infinity. For the range, I am going to grow downward till -infinity. And as I move upward, this is never going to stop growing up until positive infinity. Okay. Now, for an absolute value function, let's look at the domain to the left and to the right. As I move toward the left, this is going to keep growing to the left till negative infinity. As I move toward the right, this keeps growing toward the right, toward the positive infinity direction. Downward, it reaches a limit. The smallest y value is 0, and it touches 0, which is why I'm using a bracket. And upward, it's going to keep growing upward to a positive infinity. Natural logarithm. Domain, as I move toward the left, there's a limit as to how much I can move to the left. I'm not going to be able to pass 0, right? So I'm going to say I'm only going to be able to get to the value of 0, but will I ever get to the value of 0? Well, this is an asymptote, so I'm never going to touch 0, so I use parentheses, not a bracket, right? Here in my function, I touched 0, so I used a bracket. Here, there's an asymptote. I'm not going to touch 0, so I'm using parentheses. And toward the right, this is going to keep growing till infinity. For the range, downwards, this is going to keep growing downward forever and ever. Upward, it also keeps growing forever and ever. Okay. Exponential. So the domain, I will keep growing to the left forever to negative infinity. I keep growing to the right to positive infinity. Now, for range, as I move down into the function, am I going to reach negative infinity, or is there a stop or a limit? Well, if I keep growing and growing, I actually can't pass my horizontal asymptote at 0. So I'm going to get really close to the value of 0 as I go downward. So that's why I have parentheses 0. And if I go upward, I'm going to grow till infinity. Sine and cosine. So let's do the sine function first. So for my sine function, domain, as I move to the left, I keep growing forever to the left, right? This keeps growing forever to the left. And for the right, this also keeps going forever to the right. Now range. The lowest y value that my function touches, and it touches it repeatedly, is -1. So I'm going to say the smallest y value is -1, and the greatest y value is 1. So my range is -1 to 1. Very similar for cosine. I'm going to keep growing to the left and to the right. And my function stays within the y values of 1, -1, and 1. So again, just a really quick review on domain and range. So far, we've been observing the limit of functions on different graphs, right? Graphs, piecewise graphs. However, what were to happen if I try to observe a limit and I'm not given a graph? Is there another way, another approach to observe a limit? And there is. Today we're going to talk about what is the numerical approach to finding a limit. So we're going to start by looking at the table below. What value of x is being approached from both the right and the left side? So they give me a function. The function that creates this table of values is a function of f of x. And there's my equation for f of x. Does it make sense to say that we get closer and closer to a value, but possibly never get there? And why? So let's take a look at this function. So I can see that these values are getting smaller and smaller negatively. And then from the right, they're also getting smaller and smaller. And it seems like they're approaching this value of 0, right? And as we get closer to 0 from the left and from the right, I can see that I have the same value that they're approaching. From the left, I'm approaching a value of 0.2886. And from the right, similarly, I'm also approaching that same value. So it doesn't make sense that we get closer and closer to 0, right? We're getting really, really close to this value of 0, but never actually get there. And why? Well, if I look at the function, the equation of this function, what were to happen as I get closer and closer to an x value of 0, right? Because these are all x values. And if x becomes 0, what happens to my function? Well, I'm going to plug in 0 into my function, and we're going to see numerically what happens, okay? So I'm just copying my equation, except I'm writing down, and this is a subtraction, I'm writing down a 0 in place of x. Okay, so when I plug in 0, look at what's happening here. I get a denominator of 0. And what happens anytime I have division by 0? Well, I know that this is undefined. So I can get really, really close to the value of 0, as I can see from my table, but never actually get there. Does it make sense for this to happen? Yes. Yes, we can approach a value, but never touch it, never actually get there if there is a hole or asymptote. And that is what happens whenever I have any kind of undefined or error in my function. There is a hole or an asymptote. So we can use limits to observe what is the generic behavior around that specific value. So here they're asking me, use your calculator to evaluate the indicated limit numerically. So I don't have any more graphs. Now I have to use my calculator to observe this limit numerically. So what you would do is you would take each x value, an example 0.75, and you plug it into your function to get these values on the table. So I would have 0.75 cubed minus 1 over 0.75 minus 1. Okay. Now, if you use a calculator, I already did use a calculator, but you can definitely try to do this on your own and just double check you get the same numbers that I do. I got 2.3125. So this value goes into here, 2.3125. And I would repeat this exact same process for all of these x values. So instead of 0.5, right, I would plug in 0.9 into here and into here. Then I plug in 0.99, right? And so forth and so forth. I would plug in all of these x values to see what is the value of that function at those x values. Now, I'm so nice. I already did all the work for you. And these are the values that I got. And like I said, you're more than welcome to double check yourself and plug these into your calculator. Okay, so these are the values that I got, and I'm going to be observing the x-axis. So I can see that these x values are leading up and getting really, really, really close to the value of 1 from the left and from the right side, right? And I know that I'm on the right track because it's asking me to evaluate the limit as x approaches 1 from the left and from the right. So as I approach 1 from the left, so looking at this from the left, I'm getting really, really, really close to what looks like 2.997 is like 3. And if I look from the right side, I'm a little bit bigger than 3. So I can make the generalization that between 2.997 and 3.003, I'm getting really close to the value of 3. And I can see from the left and from the right side, they match. And so it's safe to say numerically that the limit of the function as x approaches 1 is 3. Okay? Moving on. So same thing you would do here. You would take your x value, plug it in, and then plug this whole thing into a calculator. And again, I'm the nicest person ever. And can you guys believe I crunched all these numbers in on my calculator? And there's a super fast way to do this on the TI Inspire calculators that I will teach you if you don't know already when we're in class. Okay, because there's an easy way to do this, so you don't have to do this. And it's pretty quick. So once I plug those values in, I'm going to be trying to find this limit of the function as x approaches 0. They tell me right here, 0, 0, 0. So I can see that 0 would be right about here. And so as I approach this function from the right side, I'm getting really close to the y value of 2. As I approach it from the left side, I'm getting really close to the value of 2. So the left and the right side match, and I can say that my function, the limit of this function as x approaches 0 is 2. Okay? And just for emphasis again here, if I wanted to do this numerically, I would plug in 2.9 into my function, like so. And you would do that for all of your x values. But to save us some time, I already plugged them in. You're welcome, you're welcome. And these are the values that I got. 25, negative 0.0625 again. And then I think I got lazy and I didn't do these two. So as I approach this function, I'm approaching 3. So 3 is right here. And I'm going to be approaching it from the right side. I'm getting really close to the value of negative 0.0625. And there should be a little tiny negative here, and I think we forgot it. So as I approach it from the left side, same thing, I'm getting really close to the value of negative 0.625. So we can say that because the left and the right side match, that the limit of this function as x approaches 3 is negative 0.0625. Great. Okay. Just have 2 more here. Now, for my sine function, whenever you work with trig functions, make sure your calculator is in radian mode and not in degrees. Okay, so this would be the exact same thing. I would plug in my value into f. Okay, and you already know I'm the nicest, so here you go. And I didn't do those last 2. But as I approach 0, and we know 0 is going to be right here, from the right side, I'm getting close to the value of 0. And from the left side, I'm also approximating 0, approaching 0. And so we can safe to say that my limit of the function as x approaches 0 is 0. Last one here. So you've already guessed it. In order to do this numerically, I would have to plug this in to my calculator. There it is. And I've done some of the values. I didn't do all of them. Oh, there's 3 zeros in here. My apologies. Okay. There we go. And I didn't finish those two. So as I evaluate this limit, as x approaches 0, from the right, I'm getting really close to 0. From the left, I'm also getting really close to 0. And it's safe to say that the limit of this function as x approaches 0 is 0. Thank you, everyone.